Yeah, welcome to the second part of Daniel's talk on complex numbers. His first talk in December was so popular that he had to come back and tell us more. So without further ado, I give you Daniel.
Thank you very much, Ted, and welcome back, everyone. I hope we haven't lost too many viewers from the first part, because I think today we will get into the meat, into the really interesting aspects of hypercomplex numbers. So if you did watch the first part and felt that at the end you were left at a bit of a cliffhanger, I hope to now rectify that and give you the remainder of the talk. But before I jump into that, I also just want to acknowledge that I have the distinct pleasure of doing the Christmas seminar and the New Year's seminar. So thank you very much for this opportunity to everyone at Relatorium, and also Happy New Year to everyone. I hope you had a good start. So yeah, this second part of my talk, like I said, I want to kind of get to the payoff of what we've been working towards. We did a lot of kind of the groundwork in the first part. So if there's anything in this part that you don't quite understand or have difficulty following, then I recommend you go back to the first part and perhaps you will find answers there. And it's all available on YouTube for you to watch. And I guess the other thing that I would like to try and do is to address some of the comments and questions. There were some excellent questions from the audience in the first part, and I've tried my best to incorporate some content specifically for those. And if you have questions during this part, as usual, you're very welcome to ask. And in the end, I think we will have also an extended discussion session where we can go more deeply into specific areas. So one of the questions I think in the first part that came up related to surreal numbers and how surreal numbers connect to hypercomplex numbers. And I was a bit hand wavy there because, like I said, then that's not really my area of expertise. But since then, I've looked at the Wikipedia page and I've gathered a bit more information. I just wanted to get a bit more specific. So the surreal numbers, one way to think about them is as a universal ordered field. So they're kind of the real number line on steroids, if you will, and therefore they're not quite the same kind of generalization like the one that we are talking about when we're talking about the hypercomplex numbers. It's kind of a different way of generalizing the real numbers. And if you want to do the same construction of the hypercomplex numbers, you can, of course, use the surreal numbers as your base field and then do all the same constructions that we've talked about only using the real numbers. So that's how you, for instance, end up with the complex numbers. But I don't want to go any further into that because we will have a whole talk dedicated to surreal numbers on the channel very soon, I believe. Matt will do the honors. So I don't want to take anything away from that. And instead, today we're going to go back to the hypercomplex numbers. So
just to clarify, I'll be talking about the non-standard methods, not the surreal numbers. Are two different things.
Yeah, okay. So sorry, we need to find someone else then, because clearly it is a topic of interest to talk about surreal numbers at a later stage. But yeah, thank you for clarifying that. Great. So basically, let me jump to where we left off in the previous talk. So we just finished the motivation, and I showed you some nice examples of what you can do with hypercomplex numbers, but I didn't really get to explain in detail how to do that. So this is what we're gonna look at in part 2. And in particular, I want to also show you a bit more of the geometric intuition behind the hypercomplex numbers, and also a way to reason about them in a more graphical way in using string diagram notation. So those are all things that we will look into in this part. And I guess one way you could phrase all of this is, in the first part, a lot of the material was kind of symbolic and related to abstract algebra, and it was kind of necessary to establish the foundations. But that's still very much in the worrying part, if you think about the way I phrased my title. Those are not the friendliest fields of mathematics to get into, especially as a non-mathematician. And in this part, I really hope to show the loving part. So I really started to love this subject once certain things clicked and certain pieces came together, and I discovered these nice graphical ways of thinking about things. And it made it a lot more enjoyable for me personally. So hopefully I can make it enjoyable for you as well. So just to review, in the previous part, we defined what a K-algebra is. And I have to apologize, I'm a little bit not quite precise because I use the term algebra and hypercomplex number interchangeably, essentially. But if you were really strict, hypercomplex numbers are K-algebras that are unital, so they contain a unit. And K-algebras are just the more general concept where you don't even have to have a unit inside of your algebra. But sometimes I can get sloppy and say hypercomplex numbers when technically I should be speaking about algebras. But I think the two are close enough, sufficiently close that it's excusable. And I feel that hypercomplex numbers just have a nicer intuition. They communicate better the intuition behind these higher dimensional objects that you can somehow still manipulate and treat like they're numbers. And yeah, they behave in many ways exactly like the natural or the real numbers. So we kind of built things up in the previous talk, and we explained that if you're familiar with linear algebra and vector spaces, then the only additional ingredient when it comes to hypercomplex numbers is this bilinear product that you're introducing, which allows you to take two vectors from your vector space and multiply them to get another vector as a result. And now I want to, like I said in the beginning, introduce this graphical notation that allows us to not just look at these things symbolically, but in a more graphical way. And essentially, if we have a vector that I've written here on the left, we can think of it as a point with a line originating from it. And that's kind of to symbolize that there is something that has no inputs and produces one output. And if you kind of go further to the middle, if we have something like a matrix, so a linear map in this case, or a one linear map if you want to be very precise, then you have a one input and one output in your little diagram, and that corresponds to the two indices alpha and beta on this slide. Yep, Ted, go ahead.
Quick question, or I mean, I think just clarification. The index that we use, or the label that we use next to the string, denotes the index of the input or the output. Is that right?
Exactly. Yes. Thank you. This is all kind of assuming some information from the first part where I kind of introduced this index notation. So we write our vectors as letters with upper indices, and I'm using the Greek letters alpha, beta, gamma for a generic index, which stands for any of the values 0 through n, the dimension of your vector space. And in the case of the matrix, we have one lower and one upper index. And that's a way for us to kind of remember that the way we should interpret this two-dimensional array of numbers at the end of the day is as something that we want to feed a vector into and then get another vector out. There are other interpretations which correspond to other combinations of lower and upper indices, which we will get into a little bit later in the talk. Hopefully that clarifies things. And any more questions?
And also with respect to, and you were getting to the one on the right, with the multiple matrices, am I right in thinking that there is some ambiguity around whether the two, I mean, in other words, you have made an explicit choice in the string diagram to have the two indices as inputs and one index as output, but there's nothing in the bottom description as matrices that necessarily forces that. Is that right?
Yes, I think that's a fair statement. I have kind of adopted the same conventions that we used in the first part, and I've laid things out so that everything works out nicely. If you want to take these things and multiply things out using the regular familiar matrix vector multiplication, but strictly speaking, the arrays, whether things are laid out in columns or in rows, and which axis corresponds to which index is not kind of clearly defined. But in the symbolic representation, you distinguish between upper and lower indices, and that's kind of a way to help with the interpretation. And also that's kind of the ingredient that makes the index, the Einstein summation convention work out really nicely when you have the lower and upper indices and you juxtapose two of them, then it implies a summation. And yeah, that's also something we briefly talked about in the first part. And since you already mentioned on the right, this is exactly what we encountered in our first part when we discussed that this bilinear product operation in our algebra can be described using this n by n by n array of numbers. So it's a three-dimensional array, and it has three indices to get to the coefficients, and they're called the structure coefficients of our algebra. And we represent them using a diagram like this, which has two inputs from the bottom and one output at the top. Right. So you should always read these diagrams kind of from bottom to top, with inputs on the bottom and outputs on the top. Any other questions related to this?
Well, there's a comment from the YouTube stream. It's a little bit related to an earlier thing that you said, but I want to acknowledge it. so the comment reads, so for a given ring, like the real numbers, I would like to see a surreal extension of the real numbers someday. I've noticed that such things, but I'm not familiar with much of the literature on surreal numbers. So this is just a confirmation that apparently there is in fact an interest in our audience for that type of extension. So certainly stay tuned. In February, we're planning to have Matt talk about the non-standard model of real numbers, which is along similar lines. The surreal model is yet another one, and we're going to look to add content to that effect going forward. But Daniel, please proceed.
Yeah.
Thank you.
All right, wonderful. Okay, so here I've made a little animation or representation of another way how you can think about these things. So obviously, when we write things out on a page, we have only have two axes to work with. But I guess in your mind, you can kind of picture these things as being either a one-dimensional array or grid of numbers, or a two-dimensional grid of numbers, or a three-dimensional grid. And of course, this goes on to arbitrarily many dimensions, and you can still use this kind of notation to represent these structures, even if it becomes difficult to picture them on paper or even in your mind. And one of the questions that came up in the first part of the talk was related to the fact whether or not there always has to be a unit in your algebra. So one of the most famous examples of an algebra, I think that most people are probably familiar with, is the cross product. So some of you may actually have been a bit surprised when I claimed that in the vector space, we don't have a product operation that takes two vectors and produces a vector, because that's exactly what the cross product does. And that is correct. However, it's sort of a special case. That's why I don't really count it as a general example, because it only works out really in 3 dimensions, and for some strange reason in 7, but I will not necessarily go into that rabbit hole. So in 3 dimensions, we can define a multiplication that takes 2 vectors and produces another vector, which should be perpendicular to the 2. And typically, it's defined like this. And I've used a slightly strange notation with the prefix of the cross product symbol, because I want to show in the other dimensions. So for example, in 2 dimensions, the cross product, if you use this definition, becomes just a single argument function that takes 1 vector and gives you a perpendicular vector. And in 4 dimensions, it's actually a trilinear operation. So it takes 3 inputs and produces another vector that is orthogonal. So with that in mind, how would we represent that graphically using our string diagram notation? Well, of course, we can write down the structure coefficients for each of these operations and the corresponding string diagrams. In 2 dimensions, it's just a matrix. It's a linear transformation. It takes 1 input vector and produces an output vector. In the 3D case, it has exactly the shape that we need for our bilinear product of our K-algebra or of our hypercomplex numbers. But this is one of the cases where I should really not be calling them hypercomplex numbers, because there is no unit vector.
Yeah.
No matter which vector you choose, you never get the same vector out as a result. So there is
because
no
it has,
multiplicative identity.
because it has to be perpendicular, right? So
Yeah, exactly. It's
I wonder
impossible.
if for some of the audience who might not remember immediately off the top of their heads from our conversation last time, you briefly mentioned structure constants, which is the way that you represent that sort of matrix representation of the product, of the bilinear product. Could you possibly tell us, for example, in the simplest case, in the one on the left, the matrix at the top that represents the product, which is basically those structure constants, where they come from, like the 0, -1, where those come from, just to remind us. So
Right. Well, I mean, they come from, in a sense, they're arbitrary. If we're talking about hypercomplex numbers, each collection of structure coefficients corresponds to a particular kind of hypercomplex number. And then one of the other questions that was raised in the first part of the talk is, are all of these unique, and how do I know what properties my algebra has given a certain collection of coefficients? And that is something that I will get into. But in this case, we already know what these coefficients should be, because we want them to follow this pattern, using essentially the determinant to evaluate the cross product. And the zeros and ones correspond to the fact that here we have 1 times x1 times e0, and then -1 times x0 times e1.
exactly.
And then in order to get that result, this is the corresponding matrix that you have to use. And
exactly. So that
we walked through that in quite a bit of detail in the first.
Right. I don't want to go through that all over again. Just to remind, just a connection. So literally at the bottom, what you're showing is a matrix multiplication. X now,
Yes,
the matrix is literally that matrix. It's not just
exactly.
the matrix itself, and you multiply it by that vector and you get that. So that's
Yes, exactly. That's the idea. And similarly on the right, I'm using this kind of multiplication where you pull the first argument into the outer square brackets, and then you just use regular matrix multiplications, and you can convince yourself that you indeed get the result that you expect from the cross product in 3 dimensions. And just in case you're like me and want to see what would be the structure coefficients for the 4-dimensional cross product, here they are. And it's a lot of zeros, and it's a pretty big array. I don't know if there's much else that you can take away from it, but I guess one thing that's interesting about it is that the number of real coefficients grows very quickly as you add more arguments to your k-linear map. So that's one thing to watch out for. And of course, when you have this many zeros, when you evaluate things, a lot of things will end up equal to 0. And what I'm trying to say, I suppose, is this very general approach may not be the most efficient. So if you want to evaluate just one specific algebra, you may want to specialize your code for that. But of course, if you want the full generality, then you don't have a choice. You cannot make any assumptions about what structure coefficients your algebra will have.
Daniel, I want to
Yep.
just also acknowledge a question that Matt asked on the chat stream. I will paraphrase or summarize, but essentially, as you're just showing us this example, fairly well known, at least the 3-dimensional case of a non-unital K algebra, the cross product. Whether there are other examples, or what do you know about if in the literature in general there is a tendency perhaps to call other non-unital K algebras hypercomplex numbers? In other words, that sort of approximation which you referred to earlier, is this something that one should have an eye out for in the literature?
Yeah, I think so. I think the more conventional term is to use the term algebra. One reason why I try to avoid it is because I think algebra is a pretty loaded term and it has a lot of slightly different connotations. So like I said in the beginning, I do think hypercomplex number gives you the right intuition for what it is that I'm talking about. But I think in abstract algebra literature, for the most part, people just refer to them as K-algebras or algebras over certain fields. But there is some historical precedent for using them in the way that I've been using them.
Okay, thank you very much.
You're welcome. All right, so finally, we've talked about our different ingredients, the different ways to represent k-linear maps, but now how are we actually going to put them together? So let's suppose we wanted to represent our k-algebra multiplication, which is defined by the structure constants, in this graphical notation. How would we do it? Does anyone want to take a stab at it from the audience? No ideas?
You can unmute, guys, if you want, and suggest.
Yep. This is an interactive part. Please give me your best suggestion. Or maybe, I don't know whether the question is clear, if I need to clarify the question further.
Well, I suppose maybe a hint might be that we're looking to represent products as compositions of strings, right?
Right. Somehow we want to take the pieces on the slide and combine them together so that we represent the equation z equals x times y.
So I was a little distracted because my breakfast got ready. So I will review this live stream to see, I'll roll back the live stream a moment so I can see how you did it.
Of course, no problem. In that case, I'll just go ahead and give away the answer. So essentially, the way that we compose these pieces is by connecting outputs to inputs. And if we want to represent this equation, like I was saying before, z equals x times y, we just take the x and plug it into the left leg of our structure coefficients. And we take the y and we connect it to the right leg. And then we can, in our mind, think about shrinking down this edge. So literally, physically, we can think about contracting it down so that it turns into a single point, and we end up with the same shape of diagram that we have on the left, which is just a point with a single output. So I hope that is somewhat clear.
So Daniel, it seems like, I mean, obviously we're connecting two strings. You're right. It's obvious there. But effectively, we're doing it because they have the same label for their indices.
Yes, right. So
something there.
This is how the graphical representation, the string diagrams relate to the symbolic representation. Is we draw a connection wherever we have this convention of repeated indices, which again, if you remember, implies a summation across that index.
Yeah, or put differently for people who are familiar with elementary linear algebra, it's basically a dot product. Essentially, it's a sum product.
Yes, you can think of it that way. Correct. Great. Okay, so we have these graphical ways of representing the little bits and pieces, and we have a way to combine them together to write down equations like this. So let's move on and see what we can do. So one natural question to ask is, what happens if instead of plugging in both sides, we only plug in one side and contract that? Well, as you can hopefully see from the diagrams on this slide, we end up with a two-dimensional array or a rank 2 tensor. And so we can think of it essentially as a matrix, as a linear map. So we can take some value x, multiply it out with our structure coefficients, and get a matrix representation of sorts of that number. And then we can just use the regular matrix multiplication, which we already know, to evaluate the product. So that's kind of the trick that I use when I write these things out as matrices, and when I write out the multiplication of two hypercomplex numbers as a multiplication of a matrix by a vector. The one thing that I want to point out why representation is in quotes here is that this may not necessarily be a representation in the sense of representation theory. For that, it has to satisfy some extra properties. So it works out some of the time, but not all of the time. And also I want to point out that depending on your structure coefficients, the matrix X may not be the same as the matrix Y. So whether you evaluate things by plugging things in from the left or from the right, it depends on the properties of the system of hypercomplex numbers that you're working with, whether or not these will give you the same matrices. But let's move on. So I want to get to these properties because there were some questions about that in the first part. And I showed you these Cayley-Dickson algebras, which, as you can see, as you go up in dimension, they lose some of the quote-unquote nice properties. So you start with the real numbers, which are commutative, associative, and so on. And then once you get to the quaternions, you lose commutativity, and then the octonions are not even associative anymore. So a natural question to ask is, if you have some system of hypercomplex numbers determined by an n by n by n array of structure coefficients, how can you tell whether or not these numbers satisfy some of these properties? And once again, what's really nice is that we can do this symbolically and just write out the definitions, do a bunch of rearranging, and use some index rewriting and get a relationship between the structure coefficients that has to be satisfied for this property to hold. So on this slide, this is showing the example of associativity. But
Daniel, can I interrupt for just a second? There's a question or a comment on in the chat that essentially makes me think to ask how much of this depends on the choice of basis, or is the power of this sort of index notation to make it basis independent?
That is a very good question. And essentially, this notation is basis independent, but the reasons are somewhat technical and hard for me to explain. I think I wouldn't do it justice. But essentially, since we're only working with these generic indices, it doesn't actually assume any particular choice of basis. But if you plugged in specific indices like 0, 1, 2, 3, that's when you would actually have to choose a particular basis. So if you want to know the actual values of these coefficients at a certain combination of indices, then you're essentially forced to pick a basis.
Yeah, so Matt is clarifying this. Yeah, the actual numbers that will populate those arrays will of course be different for each choice of basis, but the equations symbolically would look exactly the same because
exactly. Yes, thank you.
Yeah,
right. But so this is one of these things that takes a little bit of getting accustomed to, and especially once you get like even bigger equations and you have a lot of indices that you need to juggle around, it's not extremely friendly to work with. So in my mind, it really helps a lot to represent these things in this graphical notation, because it conveys exactly what's going on. The core idea is that associativity means it doesn't matter whether we take the first input and the second input and multiply it and then multiply the third input, or whether we multiply the second and the third input and then multiply the first input onto it. So it's really kind of obvious when you look at it in this graphical way what is going on, whereas there is a lot of mental overhead to actually track all of these indices and which ones relate to which in the symbolic representation. So that's one of the reasons why I really like this graphical representation. And you can go through the exercise for what the other kind of laws, what kind of diagrams they correspond to, and what properties, like what relationships the structure coefficients need to satisfy. But in the interest of time, I will skip over that, but hopefully this gives you kind of a flavor, a sense of how you would do it. But the next really important concept that I want to get to is the idea of an K-algebra homomorphism, because this is where things get really interesting, because this is what allows us to talk about the relationship between two different K-algebras or two different systems of hypercomplex numbers. And essentially, the idea of a K-algebra homomorphism is that you have a linear map such that if you multiply things in your first algebra and then you do this basis transformation using your linear map P, you should get the same result than if you had first done the basis transformation on X and Y and used the multiplication from your other algebra B. So this is a little bit abstract and takes a bit to get your head around, but I think it's again really nicely captured with these string diagrams, because basically what it says is if you take this linear map P and you apply it to the output, it should be the same like if you pushed it through C onto the other side, but then it changes your structure coefficients to the other coefficients from your algebra B.
So it commutes with C and D commute, essentially. That's the idea, right?
Right. Yeah. Yeah, I think that's correct. Should I elaborate any further here, or can I?
I meant C and P commute. Or yeah, okay, right.
C and D. So yeah.
So
no, sorry, I'm not sure if I'm following your comment.
No. Yes. No. You've the two products or the two operations commute. You can do one first or the other. That's what I mean. It's like I'm thinking. I'm trying to describe this in my mind as a commutative diagram.
So it's associative.
Okay.
I think that commutative diagram, that view captures associativity because you're talking about composition.
Yes, I was just thinking that. Sorry. Yes, indeed. Thank you, Matt, for clarifying.
Right. In the previous law that we looked at, that is correct. But here, I think it's a slightly different relationship. But yeah, potentially there is a way to think of it as a commutative diagram of sorts. I don't know. I would have to think about that. So there is an even nicer thing in linear algebra, if you're familiar with it, and that is if your linear map P is invertible, so it has an inverse, then you can actually take one of the P's that you applied, let's say, on the output on one side and move it over to the other side using this inverse. So you basically just apply the inverse on both sides of your equation, and it cancels out on one side and then it appears on the other. And the reason why this is really nice is if you have something like this where your linear map is invertible, you can actually express the structure coefficients of one algebra in terms of the structure coefficients of another algebra by applying this transformation. And essentially what it means is if I multiply x and y in my algebra A, it should give me the same result as if I take x, transform it using P, take y, transform it using P, multiply it in my other algebra, and then do the inverse transformation on the output.
This statement is a statement of what we said earlier, that they are independent of choice of basis, because the linear transformation would be like changing of basis.
Yes.
So,
exactly.
The invertibility of the matrix has to do with changing basis. Yeah. So if you don't have invertibility of the matrix, then you don't have that independence of the coordinate system choice.
Yes. Exactly. Yes. So similarity transformations generally you can also refer to as basis, change of basis. Yes.
But I mean, I taught a lot of linear algebra, but I never heard the term similarity transformation used in a context other than the invertibility of the matrix, because it did have to do with the change of coordinates. You familiar with the use of that term in other contexts where it actually is not invertible? Just, do you have to use something like a more Penrose generalized inverse idea to sort of capture similar kinds of things or whatever?
Yes. Yeah, I believe you're on the right track. So we will see some other examples where this is not invertible. However, in that case, we will generally just be talking about the homomorphisms, not similarity transformations. Yeah, I think the similarity transformation in this context is just something that I have imported straight from linear algebra, and it just requires an invertible, the matrix to be invertible. But yeah, so in case this was all a little bit too abstract, I wanted to really show this with an example of how does this actually work. So let's suppose you have two algebras, which we kind of saw already in the first part of this presentation. One is the split complex numbers, where you have a two-dimensional algebra where the second basis vector squares to the first one again. And in the other case, we just have the direct sum of the real numbers. So two copies of the real numbers taken together, essentially. And I've just listed the corresponding multiplication tables and written out what the multiplication operation would look like for these two algebras, A and B. And the question is, whether or who in the audience thinks that these two algebras are similar, or whether you think these are different. Does anyone have any idea? Or
I would expect that they're not isomorphic.
Thank you. Yes, that's my expectation as well, right? Because when I look at this multiplication operation, one of them is very simple. It just multiplies two numbers, and the other one has four multiplications and a sum, and it just looks unlikely that these would.
It doesn't seem like the cross term can arise from somewhere, like the x0, y1 doesn't seem to be able to be arrived at in any other way, right?
Exactly. It seems a little bit, yeah, fishy. Why should they be similar? Why should they be isomorphic? However, they turn out to be, and the proof is very simple. By exhibiting this linear transformation P, we can easily verify by simply multiplying things out that indeed, whether we do it in this order or in the other order, we arrive at the same result. And since P is also invertible, it means that the two algebras are in fact isomorphic. And this should be really interesting to you if you're a computer scientist like me, because it kind of implies that there is a way to optimize your code. Because if you think about, if you had written your software to use the multiplication, here you would do a bunch of operations that are not strictly necessary if you use this other algebra, which only requires two multiplications. Of course, nothing in life comes for free. The cost is that you have to do this basis transformation. But if you just have to do this once and then you multiply things a whole bunch of times, it might be worth the cost to first transform your basis, your algebra, to a different basis where it is cheaper to evaluate this multiplication, and then at the end you just transform back out of it.
Daniel, you know, this is analogous, very, in fact, essentially the same with the Adamar transform or gate in quantum computing, where essentially you put, you know, a qubit in a superposition of two states, and then it's easier to operate on that, and you do fewer operations on it, you know.
Yeah, yeah, and of course there are like interesting connections to quantum, computing with these matrices and things, but I won't go much into that because I don't think we have the time for it. There are a few more things that I want to show before we start wrapping up. So there is an idea that's kind of natural, which is the idea of a composition K algebra. And essentially what we want this kind of algebra to have, in addition to all the other properties from K algebras, is we want it to also include a quadratic form, which we typically call the norm. And this should satisfy the relationship on this slide. And I guess if you think back a few slides, this should look really familiar. This is almost like a K-algebra homomorphism, or it is exactly like a K-algebra homomorphism. It's just that it's a homomorphism to the real numbers, to the underlying field. So when you multiply two vectors in your algebra and you take the norm, you should get the same result like if you took the norm and then you just multiplied the two real numbers. And so in this case, of course, generally, since you're kind of going from something from a higher dimension to something that is one-dimensional, it will not be invertible. And then once we have this norm, we can also come up with a bilinear form using this polarization identity, but I think I might skip over that. But I just wanted to also mention that because if you think back to how we represented our vectors and our linear transformations and our multiplication using these diagrams, essentially the linear maps, the equivalent that we get if we just remove the outputs are generally called k-linear forms. And I've just pictured them here on the slide. And this shows one example of where the placement of the indices kind of matters.
Right. Daniel, I'm sorry to interrupt. I know you're trying to wrap up, but I think it's important for people who are unfamiliar with string diagrams to realize that that dot, therefore, that's left, you're saying you took out the output, but essentially what that means is it became a scalar. So it's
exactly, it became just a scalar.
It's now a scalar. Yeah.
Exactly. And similarly, the kind of flipped upside down vector became a covector, or an operation that takes in a vector and produces a scalar. And the bilinear form is an operation that takes in two vectors and produces a scalar. But yeah, it's slightly confusing when you just think of them as grids of numbers, because the same grid of numbers can represent either a linear map or a k-linear form. But when you look at them as diagrams, it's very clear, in my mind at least, which one's which and what's going on. So just really quickly to run through some examples of what these norms and bilinear forms look like in our familiar example of complex numbers. We've established that we have the following multiplication table. We can do this matrix representation to get this matrix. And in the end, we get this multiplication law or bilinear product operation. How would we get the norm given the information that I've provided? What should the norm be? Is there any idea or concept from linear algebra that we could use? No ideas? It's okay. I'll just go ahead in the interest of time.
Well, you just take the property you want for n on the two tables you have in front of you. You write it down. You write down those equations. You get equations that, or you get a defined function on the basis, and you linearly extend.
Mm-hmm. Yeah, I think that could work. That seems like the nice way to do it. The way that I was going to suggest is actually perhaps a bit of a hack. But if you look at the rule that we want to satisfy, so n of x times y should be the same as n of x times n of y, there is a very famous function in linear algebra that satisfies this relation. When you think of x and y as matrices, it's the determinant.
Yeah.
So the way that I would go about it is I would simply take the determinant of this matrix representation. And yeah, there are some maybe gotchas. You have to be careful. Maybe that's not always correct, but in this case, it works out very well. And you get a norm, which is exactly what you would expect for the complex numbers. So if you just multiply things out according to the way you evaluate determinants, you get x0 squared plus x1 squared. And that is indeed the right quadratic form. And then you can just use the polarization identity to get also this bilinear form, which is kind of giving you the inner product. So I just wanted to show you can follow the same procedure for the split complex numbers, and it works out just as well. And if you do this for the complex numbers, the kind of dual numbers which we used for our automatic differentiation and for the split complex numbers, and you plot kind of all the numbers with norm 1, 0, and -1, you get these nice pictures, which is kind of the first hint at the underlying geometry that these numbers are related to. And it also immediately suggests a generalization where if we can do this for -1, 0, and +1, why not do it for an arbitrary number k, let's say? So if we take this approach, we end up with the generalized complex numbers, and they work exactly the way the complex numbers do, except for this unit kappa, which I've called kappa in this case, squares to -k times the unit. And yeah, all of the corresponding functions here are derived on the slide. And you can see in this picture, it's a nice kind of continuous way to go from the hyperbola to a pair of lines to a circle. So in a way, you get a bunch of different non-Euclidean geometries unified together in one system of hypercomplex numbers. So it seems like that could be really useful. All right, how are we doing on time? Should I wrap up or should we keep going?
I mean, we're about 55 minutes, roughly speaking, because we started a little later. So maybe, what do you think? Another 5-10 minutes, something?
5-10 minutes? Okay, no worries. Sounds great. In that case, I will skip over the next part. I think this is more of a technical thing. I wanted to point out that if you actually want to apply the same idea, the same construction to higher dimensional algebras, because the ones that we looked at so far have always been two-dimensional, then you end up with not a quadratic form, but in general, a form that is to the nth power, the same as your dimension of your vector space. And in that case, you cannot quite, this slide works out just fine, except we have to replace quadratic form with, n form, I guess. However, the polarization identity doesn't work out as nicely, and you have to use a slightly more complicated looking formula, but it's not really that bad if you instantiate it for a specific case, like in this case for the dimension 3, it becomes a little bit longer, and you actually end up with a trilinear form using this more general polarization identity. However, let's move on and maybe cover one more thing. So one very natural thing to ask as well, once you've defined your system of hypercomplex numbers, how would functions look like that take an input and produce an output, an element of the hypercomplex numbers, and produce another element of the hypercomplex numbers? And one of the simplest functions you could possibly come up with is a function that just multiplies a fixed element x onto a given y. And so you could also call this the left action of x. And similarly, you can come up with a function that just multiplies from the right. And because we're not necessarily assuming that our hypercomplex numbers are going to be commutative, these two might actually give you different results. However, if you wanted to kind of visualize what this looks like, one natural way to represent this graphically would be as a vector field. So for every point in your space, you get a new vector at that point that points is the result of performing this multiplication operation. And for the unit, you just end up with this field, that vector field that just scales uniformly in all directions. However, if you pick the complex numbers and your imaginary basis vector I, the corresponding vector field that you get has this kind of rotation aspect to it. And so this all should be very obvious if you're already familiar with complex numbers, but for other systems of hypercomplex numbers, it is less obvious. Sorry.
Yeah, just to clarify, I think it is, fairly obvious visually, but just to reinforce the point, it seems like you're making a distinction superficially between the X, in this case, the base vector that's being transformed, the input vector, and then the vector, in this case, Y previously in the general case, which is doing the action, right? But in reality, you intend for both of them to be hypercomplex numbers, to be thought of as hypercomplex numbers, because so you're moving back and forth between vectors and hypercomplex numbers, right?
Exactly. Yes, exactly. I'm thinking of them as just hypercomplex numbers with the given hypercomplex multiplication. But of course, on the pictures, I'm just showing a specific system that corresponds to the complex numbers. And these complex numbers are well known. So it's not so surprising, perhaps, that the real component corresponds to a scaling action, and the imaginary component corresponds to a rotation action. But of course, in other systems of hypercomplex numbers, it's less clear. And even if we take an arbitrary linear combination of just complex numbers, the vector fields that you get, you may not have seen them before, and they are quite nice. You get these kind of spiraling vector fields. But like I said, if you go even further and look at, for instance, the split complex numbers, then you get, an entirely different vector field. And this corresponds to kind of hyperbolic rotations. So the very last point, and then I'll wrap up after this, is what the question is then, what would happen if I put a particle inside of this vector field at a certain point, and if I just let it follow the vectors of the vector field, and let's suppose I just do one big step and I advance it by a whole lot, it would end up somewhere up there. But if I shrink down my step size and I do 2 steps instead, then, I get something a little bit more interesting. I go half the distance up, and then I go diagonally. And then I can repeat this process iteratively, making smaller and smaller steps, following the vector field more and more closely. And if we take this process to its limit, then it will converge towards a nice smooth curve inside that vector field. And that is actually, if we expand that out and manipulate things a little bit symbolically, that corresponds to this limit definition of the exponential map. So the exponential map basically gives you the motion of a little particle inside of the vector field that is in turn determined by your choice of bilinear product, your choice of multiplication operation, your system of hypercomplex numbers. And it's really nice, a very general way to look at the exponential map, and something that you can do with any arbitrary choice of structure coefficients for your hypercomplex numbers.
Daniel,
so this is go ahead.
I'm sorry to interrupt. I think this is fantastic. I'm very pleased that you managed to get to this point, after the first part of the presentation. I do want to acknowledge there's a question in the on the YouTube stream, which I want to acknowledge. Essentially, it has to do with, since we're talking about basically these K algebras as K vector spaces, and with the bilinear product, whether the projection to a lower dimensional subspace be essentially embedded in K, it be, in other words, a scalar, in other words, we talked about dot products and other operations, but we haven't talked about projection as a possible operator.
Yes. I mean, that is a very good question and a very good comment. I don't know if I have a very satisfying answer to it. I do think there is more to say about operations or operators that change the dimension. I mean, one example is, of course, the norm, which does the most extreme reduction, going from your dimension n to dimension 0. But other projections...
Why dimension 0? I'm confused about that.
So, 0, because it's a point. The scalar, it takes n-dimensional vectors to scalars, right?
Right.
So scalars, but the range of n is at least a topologically one-dimensional subspace.
Okay. Yeah, but
that's real. So
yes, sorry.
Yeah, Daniel. No, but say something about this, because this is a different meaning of dimension in this case.
Yes, exactly. So yeah, that's true. So the vectors are n-dimensional. So it's easy to get these two notions confused. One is the rank of the object. So you have the scalars as your zero-dimensional objects, vectors as one-dimensional objects, and matrices as two-dimensional objects. So that's what I was thinking when I said zero-dimensional. It goes 0, 1, 2, etc. But of course, you also have vectors which have n entries, and so those are n-dimensional objects. So you can also have a one-dimensional object with one entry, and that is isomorphic to a scalar, because
exactly.
So I thought the question was more about the range of the k-valued linear form.
Right.
Okay. So in linear algebra, that range would be a subspace, a linear subspace of the base field. And so it would either be, for a field, the field has no subspaces other than itself in the trivial space. And the trivial space has only the zero vector in it. So when you say zero-dimensional, that's a different, I think it's a different focus than what the question was aiming at.
You may be correct about that.
So when you say a scalar is zero-dimensional, to me that just means you're thinking of it as a translate of the trivial subspace. So an element of the field is zero-dimensional, but the field itself is one-dimensional.
I think that's fair. So I may have misread the question.
But the range of the norm function, I'm not as familiar with general norms. But the range of the norm in Hilbert spaces and so forth, inner product spaces, is always the positive or the non-zero real numbers or something like that.
Right. So that is a very good point.
It's not even a subspace.
Thank you.
But it spans a one-dimensional subspace, the whole real line.
I'm glad you bring that up, because one of the reasons why I do not take the square root, or I try to avoid taking the square root whenever possible, is because in these generalized norms, and again, I use this term kind of not very precisely, because some of these norms will not satisfy the axioms that typically
Right.
the norm is required to satisfy. In particular, in the hyperbolic case, you can obviously get negative values as well. And then if you tried to take the square root, you would run into problems. I guess you would get a complex valued result. So yeah, that is a very good point. Thank you for pointing that out.
And I would expect that some authors probably refer to these norms as squares of valuations or something like that, because the valuation field behaves a lot like an absolute value, which is more like the norms in the inner product space sense.
Yeah. The terminology varies a little bit depending what background you come from. Yeah, in this abstract algebra sense, I guess people talk about composition algebras and quadratic forms, but then, like I said, strictly speaking, it's not always necessarily a quadratic form. It could be any power. So I don't know if there's like a really well-established terminology. There seems to still be a little bit of ambiguity, and slightly different areas use the similar terminology in a slightly different way. Yeah,
as with many areas of mathematics, yes.
Yeah, exactly. Yeah, that is correct.
Maybe we should aim to wrap up soon the live stream, and then we can continue the informal conversation. So
exactly, yeah, that's
yeah,
what I was going to suggest. So just maybe for those, like a thing for future explorations, you can use this exponential map to define things like polar coordinates, and these work well in all different kinds of systems of hypercomplex numbers. And for instance, here I've just shown a way you could parameterize this surface that results from the triplex numbers. And yeah, I think we can wrap up here. So one of the famous theorems is that really the only division composition algebras over the real numbers are the real numbers themselves, the complex numbers, the quaternions, and the octonions. So in a way, if you want a really well-behaved division and a composition algebra that has this kind of a norm operation, your options very quickly become really limited. But in my mind, I think that's a little bit misleading, because it kind of suggests that all the other possible algebras are really not very interesting, because they all end up either not satisfying all the necessary axioms, or they end up being isomorphic to one of these algebras. But even when they're isomorphic, that doesn't necessarily mean that they're not useful. For instance, these generalized complex numbers, all the values in between +0 and -1, they give you a nice continuous way to transform between spherical, Euclidean, and hyperbolic geometries, and you can do some really interesting computer graphics applications with that. And I think, yeah, that's the point where I will wrap things up, but I look forward to more discussion.
Thank you, Daniel. Let's thank Daniel. I mean, this was a really very informative, nice way to bring it all together, and to show us under the hood, as it were, how it works. So Priya, we can go ahead and stop the live stream now. And yeah, so one thought that I was having, especially towards the end, was if you think there's a way in which these notions that you were talking about can meaningfully be used in a classroom setting, for example, in a advanced linear algebra, or as an extension of